Welcome back to this course on dynamic exploitation of ILP. The question I will address in this lesson is, how can we increase the instruction fetch bandwidth so that multiple instructions can be fetched every cycle? A few lessons ago I talked about branch prediction. However, branch prediction alone is not sufficient. We must also provide high instruction fetch bandwidth. In other words, we need to be able to fetch multiple instructions each cycle. Obviously, if our processor is able to issue n instructions each cycle, then the instruction fetch unit should also be able to fetch n instructions from the instruction cache every cycle and place them in the instruction queue. Of course, fetching multiple instructions each cycle requires sufficiently wide path to the instruction cache. But this is relatively easy to solve. For example, if this is the instruction fetch unit of a single issue processor that sends the PC to the instruction cache upon which the instruction cache returns a single instruction, then this could be the instruction fetch unit of a 4-issue processor that returns 4 instructions each cycle, for example an entire cache line. However, the most difficult aspect is, as usual, how to handle branches. Consider for instance the example shown here at the bottom, where the program counter currently points to instruction 2 in cache line A, and instruction 2 is followed by a branch, and this branch branches to instruction 6 in cache line B, which is followed by another branch. Then the dynamic instruction stream that should be provided to the issue unit is instruction 2, branch 1, instruction 6, branch 2, as shown here on the right. But fetching two cache lines and aligning and merging them, all of that in a single cycle, is highly complex. The first technique to increase the instruction fetch bandwidth I will discuss is called branch target buffer. The reason for it is as follows. The branch predictors I discussed a few lessons ago only predict the branch direction, if it will be taken or not. Therefore, they only improve the performance if the branch target address, where it branches to, is known before the branch direction. In the canonical 5-stage pipeline, however, both the branch direction and the target address are computed in the second stage, the decode stage. That's why MIPS processors have a branch delay slot. But let's assume that our processor has no branch delay slot, but instead flushes the instruction fetched after a branch. Then each taken branch would incur a 1-cycle penalty, as this pipeline execution diagram illustrates. The instruction after the taken branch is flushed, and the correct instruction is fetched after the decode stage of the branch, resulting in a 1-cycle penalty. What we would like to do now is to predict the branch in the instruction fetch stage. Then a branch would incur no penalty if it is correctly predicted, as this pipeline diagram illustrates. The branch is predicted in the fetch stage, and in the next cycle the correct target instruction is fetched. This implies, however, that we need the target address at the same time as the predicted direction. The branch is predicted and its target address returned so that the target instruction can be fetched in the next cycle. A branch prediction table that stores the target address of each branch in addition to the branch prediction is called a branch target buffer. Because the next instruction address is predicted before the instruction is decoded, we must know if the instruction fetched in this cycle is a branch or not, since it can be any instruction and we do not want to branch if the instruction is not a branch. The entries in the branch target buffer therefore have a tag, very similar to a cache. In the previous branch predictors that only predict the branch direction, we assume that the branch is decoded before it is predicted. This figure shows a branch target buffer. As usual, it is indexed by some lower bits from the PC. The tag of the PC is then compared to the tag of the indexed entry. If they do not match, then the instruction is not a branch or it is not contained in the branch target buffer, and we proceed normally with the next instruction pointed to by PC +4. Obviously, only branches are inserted into the branch target buffer. If the two tags match, then the instruction pointed to by PC must be a branch, and the target address stored in the table is used as the next PC, provided of course the branch is predicted taken. This figure shows how the branch target buffer can be integrated in the canonical 5-stage pipeline. The branch target buffer, shown in orange, is accessed at the same time as the instruction cache. The multiplexer, shown in purple, is used to select the next PC. If there is a hit in the branch target buffer and the branch is predicted taken, the target address is used as the next PC. If there is a miss in the branch target buffer or the branch was predicted not taken, PC plus 4 will be used as the next PC. Not shown in this figure is the hardware needed to insert branches into the branch target buffer and to update the prediction, and hardware to recover from mispredicted branches, but this can be implemented by flushing the pipeline registers. An optimization of the branch target buffer is to store one or more target instructions instead of, or perhaps in addition to, the target address. This optimization provides two advantages. The first one is that it allows the BTB access to take longer than the time between two successive instruction fetches, which possibly enables a larger BTB. Second, buffering the actual target instructions allows an optimization called branch folding, which can be used to obtain zero-cycle unconditional branches, jumps, and sometimes zero-cycle conditional branches. This figure shows the branch target buffer after this optimization has been applied. It is identical to the previous figure, except that the buffer does not store the target address, but the target instruction or instructions as highlighted in red. In this figure, I sketch how branch folding can be implemented in the canonical pipeline for unconditional branches, that is, jumps. A multiplexer has been added to the data path. This multiplexer selects between the instruction fetch from the instruction cache and the target instruction obtained from the branch target buffer. If there is a hit in the branch target buffer and the instruction is a jump, then the target instruction is latched into the IFID pipeline register. In addition, the next PC should be target address plus 4, since we do not need to fetch the target instruction anymore, but the instruction after the target instruction. On this slide, I will illustrate using pipeline execution diagrams that branch folding executes jumps in 0 time on the canonical 5-stage pipeline. Without branch folding, but with a branch target buffer that predicts branches in the instruction fetch stage, the effective cost of a jump would be 1 cycle, as this pipeline diagram illustrates. The jump is fetched and predicted in cycle 1. Since it is a jump, it will always be correctly predicted. The target instruction, in this example an add, is fetched in cycle 1, and the instruction after the target instruction, in this case a subtract, is fetched in cycle 2. If branch folding is performed, then the pipeline execution diagram looks as shown here. In cycle 1, the jump is fetched and its target instruction, the add at address 4000, is moved to the decode stage. Then in cycle 2, the add is decoded, and at the same time the instruction after the target instruction, the subtract at address 4004, is fetched. The jump does not need to be executed anymore, so the effective cost of a jump will be 0. I finally remark that branch folding can also be used to eliminate the cost of a conditional branch, but other than jumps, the conditional branch still has to be executed to determine if the branch was correctly predicted or not. In this case, we only obtain 0-cycle execution for correctly predicted branches if there are sufficient resources to execute the branch and the target instruction in parallel. The second technique to increase the instruction fetch bandwidth I will discuss is called return address predictor. Before I discuss how it works, a little bit of motivation. All instruction sets support indirect jumps, jumps whose target address varies at runtime. Because the target address varies at runtime, the target address is obviously difficult to predict. MIPS, for example, supports the jump register instruction, which sets the PC to an address contained in a register, as shown here. Indirect jumps are mainly used to implement function returns. As you know, in MIPS, calling a function is implemented using the jump and link instruction, which stores the return address in register RA, and returning from a function is implemented by executing the jump register RA instruction. Indirect jumps can also be used for implementing switch statements, and for computed gotos in Fortran, but they are mainly used for function returns. In the spec95 benchmarks, function returns account for more than 15% of the executed branches on average, so indirect jumps cannot be ignored. Furthermore, in object-oriented languages such as Java and C++, function, in Java called method, returns are even more frequent. Of course, function returns can be predicted using a branch target buffer. However, this only works if the function repeatedly returns to the same address, when it is called inside a loop, for example. So the accuracy of prediction function returns using a BTB is low. For example, for spec95, an aggressive branch predictor achieved an accuracy of less than 60%. The problem is that a function may, and usually is, called from different places, which causes the return address to vary. To overcome the problem of low accuracy for prediction function returns, a small buffer or return addresses operating as a stack is used. Such a buffer is called a return address predictor. Every time a function is called, the return address is pushed onto the stack. For example, if a MIPS processor executes a jump and link instruction, then the return address, PC plus 4, is pushed onto the stack. Furthermore, every time a function return is executed, the predicted return is popped off the stack and used as a predicted PC. Here's an example return address predictor stack. At this point in time, there is only one return address on the stack, and the return address predictor stack pointer, RAPSP, points to this return address. Now the instruction jump and link 4000 is executed, which implements a function call. The return address predictor will then push the return address, in this case 1004, since the jump and link is stored at address 1000, onto the stack as shown here. Sometime later the function returns using the jump register RA instruction, at which the return address predictor has to produce a prediction where this indirect jump will jump to. The return address predictor will obtain the predicted return address from the top of the stack and update its stack pointer so that it points to the return address previously pushed onto the stack. Finally, I remark that if the stack is sufficiently large, meaning as large as the maximum call depth, then the return address predictor will predict the returns perfectly. This figure shows the misprediction frequency of a return address predictor as a function of the number of stack entries for different spec CPU95 benchmarks. A buffer size of 0 means that a branch target buffer is used to predict the return address. These results show that a modest buffer size works well. For example, when the number of entries in the return address predictor is 8 or more, the misprediction frequency is less than 5% for all benchmarks. These results come from a paper by Squadron and others, and this paper uses a repair mechanism when function calls and function returns are executed speculatively. Without such a repair mechanism, the return address of a function return will be wrongly predicted. Finally, in this lesson, I want to remark that in modern high-performance processors, instruction fetch is no longer a simple pipeline stage that fetches the next instruction from the instruction cache and increments the PC. Instead, it is an increasingly complex unit, the instruction fetch unit, that autonomously fetches and feeds instructions to the rest of the pipeline. On this slide, I will present some features of integrated instruction fetch unit as included, for example, in the front end of the Intel Haswell microarchitecture shown here. First, an advanced instruction fetch unit integrates branch prediction. That means that the branch predictor is part of the instruction fetch unit and constantly predicts branches so as to drive the fetch pipeline. Second, advanced instruction fetch units perform instruction prefetching in order to deliver multiple instructions each cycle. That means that instructions are fetched before they are accessed. I will discuss prefetching in the next course on advanced memory hierarchy design. Finally, when fetching multiple instructions per cycle, several complexities are encountered, including the difficulty that fetching multiple instructions may require accessing multiple cache lines. Integrated instruction fetch unit encapsulate this complexity using prefetching to hide the cost of crossing cache blocks. The instruction fetch unit also buffers the instructions in execution order. This may involve merging and aligning instructions from different cache blocks. This concludes this lesson. Thanks for watching. In the next lesson, which is the final lesson in this module on dynamic exploitation of ILP, I will discuss some limitations of ILP. In particular, I will present some results that show how much ILP is available in typical programs. Hope to see you back.